P is a proportion or a probability. Because it's a probability, it can never be bigger than what number? 1. It can never be bigger than 1, right? So because P is a probability, and let's say, for instance, P was 75% success. If it's 75% success, what's your failure going to be? 25. Thank you. I appreciate that. So if we know P, we always know Q. Do you understand that? As a matter of fact, Q is equal to 1 minus P. Everybody got that? Second property. All trials are independent. All trials are independent of each other. We are funny. All trials are independent of each other. What does the word independent mean in probability? It means to multiply. So we can multiply probabilities, what this is telling me, all right? And the final thing, and the most important thing to distinguish this, is that there are a fixed number of trials. There is a fixed number of trials.
No, it's R.
You sure? Okay. There are a fixed number of trials. And we call those fixed numbers, that fixed number of trials, we call it N. We call it N. I will. All right, if these things hold, then, if we have these things met, if these three things are met, then we can say this. We talk about the random variable x, and we say that random variable x, this symbol means follows, or approaches. It follows or approaches a binomial variable. It's a binomial variable. We use letter B. And then we state what we call parameters. Y'all remember what parameters are?
No.
Parameters are true values, the true values. Approaches the parameters, has parameters N. What does N stand for?
Number.
Fixed number. And then P. What does P stand for?
Success.
If I know P, I also know Q. Everybody got that? So if these three things hold, we can make this statement here. And we can find probabilities with that statement. Establish some of this notation for this. But the notation reads like this. Here's the things you need to have for a binomial. You need to know what P is. So P is equal to the success rate. And Q is equal to the failure rate. N is the fixed number of trials. And then we're going to do one more variable which we call X. Capital X, bless you. Capital X is going to equal to the number of successes. So capital X is the number of successes you have here, right? And so the first thing you have to do with any binomial problem is actually establish that it is binomial. And you're going to check three things again. Make sure you have only two outcomes, success and failure. Make sure that each trial is independent, and make sure you have a fixed number of independent trials, all right? So look at the example. Decide the following scenario is binomial. If it is, state the values of P, Q, N, and X. So first one says, a basketball player has a 60% chance of making each free throw. What is the probability that the player makes exactly 2 out of 3 free throws? So let's start here, all right? Is this binomial? The first thing we need to do is identify whether there are only two outcomes. Are there only two outcomes for the scenario? What are they? Either he makes it or he doesn't. So those are the probabilities, right? So that means that our P is equal to what then? Our P is either he makes it or he doesn't, but it tells he makes it at what rate? He has a 60% chance. So our P is what? 0.6. And our Q, that makes our Q equal to what then? 0.4. Everybody understand that, right? So he has a 60% chance to make it, a 40% chance to miss it. That's what the problem says. So we reduced it to success and failure. That's the first part. Now, next thing, is he taking a fixed number of shots?
No.
Look at it again. Is he taking a fixed number of shots?
Yes.
How many is he taking? He's only going to take 3 of those shots. So that's at fixed numbers what we call what? N. So N is equal to 3. The last part is to make sure that the trials are independent of each other. Should one free throw affect another free throw? If I make or miss the first, does that affect me making or missing the next one? No. So, are they independent? Yes. And here's what we're going to write then. Here's a statement we can write. X follows a binomial distribution with an n of, what's your n? 3. And your p is 0.60. Now, they want me to find the probability that he makes what?
2.
Exactly 2 out of how many?
3.
3. So that means that my big X is equal to what? The number of successes I want are, what's the number of successes I want? 2. I want exactly 2 successes. Everybody understand why? Now, so how is B different? A basketball player has a 60% chance of making each free throw. What is the probability that the player's first made shot occurs on his 4th free throw attempt? How is this different than letter A? Well, let's go through it and see real quick. Is there a probability of success or failure here? Yes. What's the probability of success? 0.6. What's the probability of failure? So is that different? No. Next thing. Will one shot affect another shot? Yes or no?
No.
So the independence factor is not different. Everybody got that? But then the question asks us, what's the probability that his first made shot occurs when? On his 4th free throw. Does that mean he have to make it? Does that mean he has to make it on his 4th free throw? No. We just want to know if it's going to occur on that 4th free throw, right? It could technically occur when? The 2nd free throw, which would stop it. Does everybody understand that? It could technically occur on the 1st, which would stop it. And it could technically occur on the 5th, which would be past the 4th. Do you understand that? So what don't we have here? We don't have a fixed number. And because we don't have a fixed number, and we're interested in the number of failures until we get our first success, we want to know how many times does he fail before he gets his first success on the 4th free throw? This is what we call a geometric distribution. This is geometric. And in this case, here's what you're going to do for a geometric. It's simple. It's a simple probability problem. I'm not going to give you a formula for it or anything. But how many shots does he take before he makes his first free throw? You want to make 4. You want to make it on your 4, so you have to miss how many first? 3. And then that last free throw, what is he going to do? That last shot, he's going to make it. Well, these shots are still independent of each other, right? So what can we do to the probabilities? What can you do to the probabilities when they're independent? Anybody?
Multiply.
Thank you. You can multiply. So we take the probability of failure, 0.4 times 0.4 times 0.4 times. And then that last one on that 4th shot, what does he do? He makes it 0.6. So if we multiply these out, here's what we get. 0.4 raised to the 3rd times 0.6. I get there's a 0.0384 chance that that's going to happen. Or a 4% chance that it'll take 4 free throws before he makes his first one. But notice those are different types of probabilities. Why are they different? One had a fixed number and the other one didn't.
What does that say? 0.03?
84. So using the part A of that, let's go down here to this binomial formula box and generate the formula for it. It says a basketball player has a 60% chance of making each free throw. What's the probability that the player makes exactly 2 out of 3 free throws? The first question you're going to ask yourself is this. Do we have success failure again? Yes. Is there are the shots independent of each other? Yes. Is there a fixed number?
Yes.
Everything for a binomial. Everybody got that? Here's what we're going to do. How many shots does he take total?
3.
3. So we'll draw out 3 blanks. And then let's represent the first shot, second shot, third shot. Everybody got that? Out of these 3 blanks, how many does he have to make? 2. So let's let the first 2 be 0.6, so that's the probability of making it. And the last blank will be what? 0.4, because that means he missed it. This is exactly 2 shots out of 3. Does everybody understand that? So we calculate this 0.6 squared, or 0.6 times 2. Plus, 0.6 times 0.6. Not 0.6 times 2. 0.6 times 0.6 times 0.4. Because we can multiply them out, we get this value right here. 0.144. But the problem with this value is this. This only says that he makes the first and he makes the first and second and misses the third. Does everybody understand that? Is that the only way to miss 2 shots out of 3 though? How else can you do it? So we miss the first and then make the other back 2, right? So we could do like this, missing the first, that's 0.4. Then making the back 2 would be 0.6 times 0.6. How is that different from what we just calculated? It's not different. Good. They're not different. They're the exact same values. This is 1.144 as well. Does everybody understand that? Is this the only way to make 2 shots out of 3? There's another way, right? How can we do this one? This time we can miss the what? Miss the second one and make the other 2, right? And that's equal to what? Thank you. 0.144. Which gives me, now I can find the total by adding these up. And if I add these up, I get 0.144 or times 3, and I get 0.432. Everybody got that? Now, the process of finding the different ways that we can make 2 shots out of 3, this process right here, how many ways did we generate, by the way? 3 different ways. Everybody got that? It's called a combination. So there's a combination of ways you can make these. We kind of came up with 3 different ways before we exhausted all the ways there are. So we're going to use this notation in combinations and come back up here and write this down. And a combination is going to give you how many ways you can reorder the successes and failures. So the combination gives how many ways to reorder the, and I'll call it P and Q. You know what that means, right? Success and failure. So how many ways can we reorder P and Q? In our case, we got 3. We use a formula for that. And that formula is called N choose X. Where, what does N stand for again? The fixed number. And what does X stand for? So in our case, it would have been what? What's our N for the basketball player? It would have been what? Our fixed number was what number? 3. Our number of successes I wanted was what? 2. So this would have been 3C2. I'll make it bigger. Hold on. We can also write this NCX part. Instead of writing NCX, we can write it like N over X, like this, in parentheses. That's the same notation. They both mean N choose X, though. And you have this function in your calculator. All right, so you don't have to do it by hand. You're going to do it with the calculator. And in your calculator, here's how you find it. Y'all have your calculators? Yes. And you don't get you don't grab one of the TI-84s. Get an 84. Grab an 84. Don't grab the gold one. Grab 84. In your calculator, if you press the math key, let's go find the function real quick. Press the math key. And arrow over to PRB. And in PRB, do you see NCR? That's NCX. It's the same thing for us, all right? To use it, here's how you use it. You always write N first. What's your N? 3. Math. And then you go to PRB. So press math PRB, and then go to NCR. And you get 3C2. So you always write N first, so you understand that. So put a 3 first, and then what do you press?
3,
Math, PRB, NCR.
But whenever I press enter, it says error.
Don't press, you print NCR?
Yeah.
Do it again. It said error again. Oh.
Can you press
It just says 3 NCR, and then I press enter.
No, and then
it
press
says
2.
error.
You got to press 2 after that.
Okay.
So once you do that, press the 2, and it'll give you a value of 3, which is the number of combinations we needed. Does everybody understand that? So once we have our combinations, here's how it works. We're going to generate a formula for this. And here's the formula we're going to generate. We know that for NCR, NCR produces the number of ways we can rearrange these things. We can rearrange this how many different ways? 3 ways, right?
Yeah.
1, 2, and 3. How do we get this 0.144? We multiplied what? P by Q. Everybody got that? So we got that 0.14 by multiplying P by Q. So in this formula, we know we have to have this. We need to have some combinations, NCX. And we know we have to multiply P by Q. Now, how many times am I going to multiply P and how many times am I going to multiply Q? That's the next question. Well, in this case, we multiplied it by, so 3C2, we multiplied P, which is 0.6, by how many times? 2 times. Why 2 times? Good. That's how many times we wanted. That's how many successes we wanted, right? And that left us multiplying 0.4 by what? We wanted 2 successes out of 3, so that means you have to have how many failures? 1 failure. So we're going to generalize this formula down here now. NCX gives the number of combinations. P times Q tells me my multiplying probabilities because they're independent. The number of P's I'm going to have is based off the number of successes. What do we call success? What letter stands for success? X. So this is P to the X. So you have P raised to the X. That means you're going to have P that many times. And then Q is going to be raised to the what? RQ is raised to the first Y. You only have 1 failure. If you have 5 things and you wanted exactly 2, how many failures would you get now? If you have 5 failures and you only wanted 2 things, right? Or if you had 5 total things, I'm sorry. If you had 5 total things and you only wanted 2 successes, how many failures would you have to have?
3.
Why? That's what's left over, right? So do it with this right here. If you have a certain n amount of things occurring, fixed number n occurring, how many failures are you going to get? How do you get the number of failures from that?
Minus.
Good. N minus what?
1.
How many successes, right? Failure is going to be equal to n minus the number of successes that you had. If you have 5 total things and you want 2 failures and you want 2 successes, that has to leave you with how many failures?
3.
3. 5 minus 2 is 3. We had how many things here? 3 things, right? We wanted how many successes? 2. That left us with how many failures?
1.
You understand that? 3 minus 2 is 1. So that's what this is the actual binomial formula that you just calculated. That's the binomial formula.
What does it say up there?
Which part?
I can't see what's over PQ.
X and n minus x. Because I missed that. I forgot to talk about the mean. So the mean of a binomial, we call it mu of x. Mu of x for a binomial is equal to n times p. The mean for any binomial is n times p. And I'll give you an example why it's n times p. Let's flip a fair coin. Let's flip a fair coin. What's the probability of a fair coin landing heads? 50. Or 50%, right? You got that? What's the probability of a coin not landing heads then? 50%. It's 50-50. Everybody got that? If I flip that coin 100 times, how many heads do I expect to get? 50. Is that a binomial scenario? Yes or no?
Yes.
Do you have a fixed number? Yes. Probability of success and failure?
Yes.
Are flips independent of each other? Yes. That is binomial. In the calculator, you just did n times p. You multiply 0.5 times 100 and it got 50. That's what you're doing. So that's how you calculate any binomial experiment, though. The mean for any binomial, or the expected for any binomial. The standard deviation for a binomial is equal to the square root of NPQ. Standard deviation is NPQ. So you take the expected number multiplied by the failure rate, and then take the square root of that. That'll give you the standard deviation. I forgot to talk about that a second ago. Now, here's what we're going to do, though. We're not going to do these by hand. We're going to do these with the calculators. So you need a calculator for this. If you don't have one, get one. But we're going to talk about 2 types of binomials today. We're going to talk about what's called binomial PDF. The binomial PDF in your calculator. And it's located, and PDF means the probability that x is equal to something. So when you see words like exactly 2, in this case, the probability that x is equal to 2. Exactly 2. Let's find it in our calculators. In your calculators, if you press the second key and you press vars, or DISTR. Do y'all see that above bars? Second. And vars. Y'all see that? Everybody see vars? Click on it. Do you see binomial CDF or binomial PDF and binomial CDF? Y'all see those? There's two functions. You need to know which one to use and when to use it. You're going to use the PDF when it says the words equal to or exactly. Do you understand that? In this case, are we using a PDF or a CDF then? PDF. So the PDF wants you to do this. When you talk about equal to, you're going to do binomial PDF. The calculator wants you to give it three things. It wants a fixed number n, it wants a probability of success p, and it wants to know how many successes you want x, and it'll do the rest of the work for you. So in our calculators, we're going to go binomial PDF. We're going to go binomial PDF. What is the fixed number? 3. And use your comma key. I know y'all see y'all comma keys? 3. What is the probability of success?
50.
What's the probability of success for this problem? 0.6, right? How many successes do I want? 2. Close the parentheses. Press enter. What do you get? Which is what we did by hand, right? Y'all see that? But your calculator is going to spit it out for you. Do you understand that? So, look at example A. It says the probability that a light bulb is defective is 10%. What's the probability that exactly 3 of 8 light bulbs are defective? So first thing we need to do is make sure this is binomial. Is it binomial? Do we have a probability of success and failure?
Yes.
What's the probability of success here? 10%. What's the probability of failure? Do you understand why 10% is success and not failure this time?
Because you want it to be defective.
Good. You want it to be defective. You're looking at the light bulbs that are defective. So the probability of success here is actually P is 0.1, which makes N, what's N equal to? Do we have a fixed number? N is equal to what here? 8. Right? And X is what? I want exactly 3, so X is 3, right? So we say this, here's how we're going to write this. The probability that X equals 3 is equal to binom PDF. Why are we using the PDF? It's equal to. What is your N? 8. What's your P? 0.1. What's your X? 3. So go to your calculator. Binomial PDF, 8, 0.1, and 3. What do you get? Thank you. So this is equal to 0.033. I want you to try letter C. Try letter C next. So for this one, suppose that 30% of employees in a large factory are smokers. What is the probability that there will be exactly 2 smokers in a randomly chosen 5-person work group, right? So what is there a fixed number here? What's N equal to? N equals 5. Is there a probability of success? Is there a probability of success?
Yes.
Which is P, which is what here? Probability of success is 0.3. Is this right here? Person smoking is what you're interested in. Is there a, what is the number of successes that I want? X equal to what? 2. So I want to calculate, you need to write these statements too, by the way. The probability that X equals 2. That's what you're calculating. And that's equal to binomial PDF. Your N.
5.32.
Good, 5. 0.3 for a P. Your X is 2. So we calculate that.
Equals 0.3.
5.3 and 2.
Please tell me the homework is like
No. just not all of it. 0.3087. So that's when it's equal to. There's another function you calculate called Binomial Cdf. I'm about to tell you. And you use Binomial Cdf when you're calculating at most or up to. So when you calculate at most or up to. And what that really means is you're doing the probability that x is less than or equal than something. And if you look at B, I'll show you what I mean. The probability that a light bulb is defective is 10%. What is the probability that at most 3 of 8 light bulbs are defective? What does it mean at most 3 of 8? What does that mean? No more than what? 3. No more than 3. Does everybody understand that? Can I have less than 3?
Yes.
What can I have? I can have what? 1. I can have 2. I can have 3. Or I can actually have 0, right? Because it can be 0, 1, 2, or 3, when you write the probability that x is less than or equal to 3, what you're really writing is the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3.
Hold on, let me write that.
The question is this. Don't write all that down. Don't write all of that. Just wait. The question is this. We know how to calculate this right here, right? We did it up here. Do y'all see that? This was x equals 3. Do y'all see that? How would you calculate 2? Just change the 3 to a what? How would you calculate 1? Change the 3 to a 1. How would you calculate 0? So that means you have to find it 4 times and add them all up. Y'all got that? There's a quicker way to do that, though. And the quicker way is to do this. Is to use Binomial Cdf. And the Binomial Cdf is going to say this. I have n, 8 things. Probability of success is 0.1. But I want to add all those numbers up to what? Up to 3. Up to 3 successes. So that's going to capture 0, 1, 2, and 3 in the calculation. So when we do that, we get second bars, Binomial Cdf.
Hold on,
So you're doing CDF this time. Why are you doing CDF?
because
It's at most, it's less than or equal to. So we're doing CDF. 8.1 and 3. And you get this right here.
0.99.
And I'll show you why. If you watch what happens when I add up all 4 of them in front of it. Binomial PDF. 8.10 plus 8.11 plus 8.12 plus 8.13. So this is all 4 of those binomials added up. Do y'all see that? Look what I get. The exact same value. So the function is going to calculate that by just adding them up for you. Do you understand that?
How many decimal places do we put?
Go to 3. So 0.995. So I want you to try to do D. D says at least, but I want you to change it to at most. Change this to at most and try to do D, please, real quick. We're going to do the probability that x is that at most 2 smokers, so x is less than or equal to 2, is equal to binomial. And again, because it's at most, you're using the CDF. Your n is 5, your p is 0.3, and your x is 2. What'd y'all get?
0.837.
What'd you get?
0.837.
Thank you, 0.837. Good. We'll stop there.